Welcome back, everyone. So, what I would like to talk about today is a particular kind of sum called a Riemann sum. And to set the stage, I want you to consider with me the following scenario. We've got the function here, f of x equals x squared, and we're going to draw it only over the x values from 0 up to 2, and that's pictured down here on the bottom right. Consider the problem of trying to calculate this violet shaded area that's squeezed between the graph of the function and the x-axis. Do you have any ideas about how you would calculate the area? Well, there are a variety of methods here. It looks almost triangular, this region, but not quite triangular. If we tried to approximate it using 1/2 base times height, that would unfortunately be an overestimate. Some folks have had the idea of maybe zooming into this grid here and trying to count the number of shaded boxes in the grid, and that's another perfectly valid way to get an estimate for this area. But what we're going to try and do is build up a technique that we can use to actually calculate this area exactly, no matter how bizarre, really, the function f may be. And the idea is this. It's hard to take the area of a general shape, but it's easy to take the area of a rectangle. The area of a rectangle is just the length times the width. So what if we sort of overlaid some rectangles onto this region? What if we tried to tile this region using rectangular shapes and then find the areas of each of those rectangles and then add them up, and that should give us an estimate for the area as well. Now at first glance this may seem like a really bad way to estimate the area. We're going to figure out as we go forward ways to use limits to make this a really good approximation. Now suppose that we start out and we use only 4 rectangles to estimate the area here. Let's see what the estimate of the area would be if we calculated the area of each of these 4 tiling rectangles and added those areas up. So rectangle 1, that's this little guy here on the bottom left. Now this rectangle here on the bottom has a width of 0.5. That's the difference, the change in the x values going from the first 0 to the second endpoint of 0.5. Now meanwhile, the height of this rectangle is interesting because the upper portion of this rectangle actually is anchored to the graph of f of x at the point x equals 0.5. The height of this rectangle is f of 0.5. And so I could find the area of rectangle 1 by taking f of 0.5, the height of that little rectangle, and multiplying it by the change in x, by the width. Rectangle 2. Rectangle 2. Rectangle 2 has exactly the same width as did rectangle 1. Rectangle 2 has a width of the change in x, an increment of half a step from 0.5 to 1. But the height of this one is different. The height of this second rectangle can be found by plugging x equals 1 into the function. That is how high this rectangle is. Rectangle 3, let's write down the area for rectangle 2 real quick. The area, once again, will be the width times the height, so f of 1 times this delta x. Rectangle 3, can you guess what the area would be? The width is still the same, delta x equals half a step, 0.5, and the height, it's now anchored to the graph at x equals 1.5. f of 1.5 times delta x. And as well, here for the fourth largest rectangle, we would have rectangle 4 with an area of f of 2 times this step of delta x. Now, if we add all of these together, we will have an estimate for the total area under the graph, f of 0.5, f of 1, f of 1.5, f of 2, each of those multiplied by this step length, by the width of delta x equals 0.5. This would be an estimate. Now this was an extremely bad estimate, and we can see just how much of an overestimate it is, because much of these rectangles are exceeding the region that we want to estimate. But if we, instead of taking 4 rectangles, if we took 8 rectangles, if we took 16 rectangles, if we took 32 rectangles, we can see from these images here that the more rectangles you take, the better approximation we will have for the area under the graph. The more rectangles you use to do this tiling, the better the approximation for the area. So what we're going to do in the next video is we are going to find a general formula that can be used to estimate the area under the graph of a function using however many rectangles you want to use. And that will be a formula for the so-called Riemann sum.